Hello my dear students, welcome to video number 145 of my channel MALACHEMPHILIC. And this video number 145 is the episode number 84 of Chemical Thermodynamics. And here the topic is Thermochemistry part 10. And this is the last part of Thermochemistry. And this part is the continuation of the earlier part, that is Thermochemistry part 9. So you have seen in Thermochemistry part 9 I have discussed the concept of Born-Haber cycle. So this part 10 is the continuation of Born-Haber cycle, where I am going to discuss different numerical problems based on Born-Haber cycle. So let's start. So Born-Haber cycle, already I told you that this Born-Haber cycle, it involves the formation of 1 mole of the ionic solid in the standard state. Okay, and it works, and it relies on this Hess's law. What is Hess's law? That is, enthalpy change of the reaction is independent of the path. So this formation of this ionic solid, if it occurs in one step directly, then whatever be the enthalpy change value, that will be same as that of the sum of the enthalpy change values in the different steps involved in the indirect path of Born-Haber cycle, right? And already I told you last video also, I told you here some mistake is there. This will be gas, and here also this will be, this will be gas. Okay, so, and there are different steps, that is sublimation, ionization, dissociation, then electron affinity, and this lattice energy, which is the enthalpy change when 1 mole of this ionic solid is formed from the constituent ions, cations and anions. And I also told you this lattice energy cannot be measured directly. You can measure this enthalpy change of this formation, but lattice energy cannot be measured directly. So the application of Born-Haber cycle is to calculate this lattice energy of this ionic solid. Okay, so let's see. Now, last video I have given this problem for you so that you can solve this problem, and I told you I'll give you the solution in the next video. So now I'm going to solve this problem. What is the problem? Calculate the bond energy of this XX bond, that is halogen bond, from the given data. What are the data given? That is dissociation of the ionic solid to the metal ion and X minus ion, both are in the gaseous form. Okay, so this is the reverse of this, your lattice energy. Okay, lattice energy, formation of this ionic solid from the gaseous ions, and this is the reverse, that is a dissociation. Okay, that is given here. And other things, that is the sublimation energy is given, then this ionization energy is given, then the dissociation of the XX bond or atomization, this we have to find it out, and then this formation of the X minus anion from the X gaseous atom, that is electron affinity value is given, and finally this enthalpy of formation of this ionic solid from the constituent element, that value is given. So we have to find out this bond energy of XX bond. So directly we'll apply to this Born-Haber cycle. What is that one? That is delta HF naught, that is equal to, you know, first of all we have to take the sublimation, that is delta H0 sublimation. Okay, after that this ionization, that is delta H0 0 not ionization. Okay, then after that this dissociation of the halogen, that means plus half bond energy of this XX bond. After that what? Your this electron affinity, so formation of anion, therefore plus delta H naught electron affinity, okay, and plus this value, that is here it is given as dissociation, but I have to take the lattice energy value. Okay, so I'll write plus U. Lattice energy generally you denote by U. Okay, now we'll put these values. What are the values? Enthalpy of formation value is minus 400 is equal to sublimation value is 100 kilojoules per mole. Okay, then ionization value is 500, right? And then we have to determine this one, that is half bond energy of this XX bond. Okay, now plus this electron affinity, which is negative, energy is released, so minus 300. Okay, plus this one, this lattice energy. Here it is given dissociation, but lattice energy means energy is released during the formation of ionic solid. And here it is the dissociation of the ionic solid to gaseous ions. So I have to take it as minus, negative. So minus 800. So therefore, this, if I calculate this one, half bond energy of XX bond, that will be is equal to, so minus 400, and then if it goes this side, so minus 100, minus 500, then plus 300, plus 800. So therefore, this half bond energy of this XX bond, that will be is equal to, this is 900,000 minus 1000 plus 1100, that means it is plus 100. So therefore, this bond energy of this XX bond, that will be is equal to 2 into 100, that means it is 200 kilojoules per mole. Hope you have got this answer when you have solved this one. Now, next problem, that is problem number 2. What is problem number 2? Calculate the net energy change in kilojoule per mole when solid magnesium fluoride is formed from its element, and this equation is magnesium solid and fluorine gas, magnesium fluoride solid. Sketch a Born-Haber cycle for the process. What and the given values are delta H sublimation value is given, ionization energy 1 and 2 because magnesium plus 2. So plus 1 and then plus 2. So both the ionization values are given, and this dissociation of this fluorine, that value is given, electron affinity value is given, and this lattice energy, this value is given. Direct problem. Okay. So calculate the net energy change. So what is there? First one is, we'll take the, that is the sublimation. Okay. So this magnesium solid to magnesium gas, and this is our delta H sublimation, and this value is how much? 147.7 kilojoules per mole. Okay. Next, ionization. First ionization and second ionization. So, magnesium gas Then this ionization energy 1, first ionization. So magnesium plus gaseous form, and this value is 737.7 kilojoules per mole. Fine. Next is formation of divalent magnesium or magnesium plus 2. So magnesium plus gaseous form, then it is ionization energy 2, and then the formation of magnesium plus 2 gas, and this value is how much? Ionization 2 value is 1450 kilojoules per mole. Next, coming to the non-metal part, that is fluorine gas. And this undergoes this dissociation. So that dissociation, we'll write this one, delta H dissociation. Okay, this is dissociation. So here, two fluorine atom in the gaseous form, and this value is given as 158 kilojoules per mole. Now, electron affinity. Electron affinity of two fluorine atom. That means your two fluorine gas, then this electron affinity for one electron affinity for one fluorine, it is minus 328 for two fluorine atoms. So it will be double of it. That means it will be here, this value will be here minus 656 kilojoule. Okay, so this two fluorine gas, sorry, here I didn't write, two fluoride ion gas. Okay, and then the last one, that is the lattice energy. Lattice energy means this magnesium plus 2 gaseous form. So magnesium plus 2 gas plus 2 fluoride ion gas. Okay, that is forming the magnesium fluoride solid, and here the value is minus 2957 kilojoules per mole. Just to add it, what we are getting, look at here, magnesium gas this side and the opposite side getting cancelled. Magnesium plus gaseous this side and opposite side getting cancelled. Okay, then your magnesium plus 2 this side gas, and here also opposite side cancel. Then your what is there now getting cancelled? This twice F gas, this twice F gas this side and twice F gas this side. This is also getting cancelled. Then now twice F minus and this side and twice F minus this side is getting cancelled. So what is left over now? Left over is, this is magnesium solid plus fluorine gas, this fluorine gas that is forming. That means this one is left over and this fluorine gas is left over, and that is forming the magnesium fluoride solid. So this is our formation, magnesium fluoride solid from magnesium solid and fluorine gas. And so if you add it, then this value will come minus 1118 minus 1118 0.9 kilojoules per mole. So this is the answer. Now coming to the third problem. The formation enthalpies of, that is delta HF naught, of hydrogen gas and oxygen gas are given 220 and 250 kilojoules per mole at 298 Kelvin, and the formation enthalpy of water in the gaseous form is given at the same temperature. You have to calculate the average bond enthalpy of OH bond in water. So let's write the equation. So we know that hydrogen gas plus half oxygen gas, and that is giving you this formation of this water, and here it is in the gaseous form. Okay, right? And they have given the formation of this hydrogen means atom hydrogen gas, that value they have given, and here two hydrogen atom is forming, so this value will become 220 into 2. Here it will be delta H will be 220 into 2, right? And then from here your one oxygen atom is forming, okay, and that value, this here the delta H value is 250. Yes, for oxygen it is 250. So this is gas, okay. So this two hydrogen atom gas plus one oxygen atom gas, they are forming this water, okay, where two OH bonds are there, and here energy will be released because forming this water molecule. So energy will be released, so minus, and two hydrogen oxygen bonds, so bond energy of this 2 into bond energy of this oxygen hydrogen bond, right? So now therefore this delta HF, that is enthalpy of formation, standard enthalpy of formation, this value, that is equal to your 2 into 220 plus 250 minus 2 bond into bond energy of the 2 OH bond, okay. And now this value is given how much? Minus 242 kilojoule per mole. Minus 242 is equal to, this will be 044 plus 250 minus 2 bond energy of oxygen hydrogen bond, okay. So 2, if I take this in this side, then here it will be 2 into bond energy of this oxygen hydrogen bond, that will be is equal to 242 plus 440 plus 250. So how much it will be? 440, 250, 690 plus 240. So 932. 932. So therefore, this bond energy of this oxygen hydrogen bond, that will be is equal to 932 divided by 2. 932 divided by 2, so 4, then 6, then once again 6. 466 kilojoules per mole. So kilojoules per mole. This is the answer, right? Now coming to the last problem. Calculate the lattice enthalpy delta HEL, or you can write it as U. Okay, of lithium fluoride. It is direct problem, application of Born-Haber cycle. Lithium fluoride from the following data. Enthalpy of sublimation of lithium is given, enthalpy of ionization of lithium is given, bond dissociation energy is given of fluorine, and then electron gain enthalpy, that is electron affinity value, is given, and overall enthalpy of formation is given. So directly we will put it in the Born-Haber cycle, that equation. So our delta HF0, that will be is equal to delta H sublimation, then plus this ionization enthalpy, that is your plus, I'll write delta H ionization. Okay, then this bond dissociation, that means plus half the dissociation of this fluorine bond, fluorine bond, right? After that, if your value is electron affinity value, that is plus EA, I am writing EA, electron affinity value, and after that will come the lattice energy U. Okay. So we have to calculate, all these values are given, we have to calculate the lattice energy value. Okay. So here U will be is equal to delta HF naught minus your delta H sublimation minus delta H ionization, okay, right, that is minus half of this dissociation of this fluorine bond, this minus, or I write electron affinity, minus electron affinity, and that's all, no, this, and minus electron affinity. Okay, fine. So U will be is equal to delta HF0, that means formation enthalpy. How much it is? Minus 594. Minus 594. Okay. Then sublimation. Sublimation, you have to supply energy, so positive, but here it is negative sign. So it will be minus 155.3. Right. Next is your ionization enthalpy. Here also energy should be supplied, so it is minus, that means it will be minus 520 kilojoules per mole. Okay. Then this value, that is dissociation of this fluorine, that will be also minus 75.3. Okay. Then your 75.3, then this is your electron gain affinity, so this is already minus, so here it will be your plus 333. Okay, so this everything is correct, no? Fine. So U will be is equal to, then if you calculate this one, minus 594 minus 520. So if you calculate this one, it will come 1011.6 kilojoules per mole. Fine. So This is the answer. So these are the problems based on Born-Haber cycle. So hope you have enjoyed. Thank you.